Circuits. First, let's define electric current. We've talked about it in the previous slides, but now let's define it. Electric current is the rate of flow of electric charges or charge carriers through a medium. And what's a medium? Well, we're going to use copper wires. Okay, those are the wires that are in your wall in your house, and also the wires that lead from the wall into various equipment such as lighting fixtures, vacuum cleaners, stereos, etc. Current, and that's what we're talking about here, is defined as the amount of charge, delta Q, that flows past a location in a material per unit time, delta T. And we use the letter I for current. Delta Q is the amount of charge, and delta T is the time it flowed past the location. The current will depend on the type of circuit elements in your circuit and their resistance, there's that word again, and we'll be talking about that soon, to the flow of charges. The charges don't go through there without interacting with the materials in the conductor, and there'll be varying degrees of resistance to that flow. The current, which is delta Q over delta T, has units of coulombs, right, because that's the unit of charge, per second. This can be rewritten as amps. 1 ampere or 1 amp is equal to 1 coulomb per second. And maybe you've heard people talk about amps. Hopefully you've heard about volts, and amps is another key part of your circuit. It was named after a French physicist, Ampere. It's a little tricky to understand electric current because you really don't see it if it's working right? It's inside the wires, inside your equipment. If you ever do see it, you're in trouble, right? That's lightning. Or if you have a downed wire from a power line, you do not want to see current. And you'll see it as big sparks. Not cool. So let's consider an analogy. This isn't perfect, but it'll help give you an idea. The flow of water molecules is similar to the flow of electrons, and the electrons are the charge carriers. Those are the particles that are moving through your wire. Your water flow depends on the pressure exerted on the molecules, and you can either get that by a pump, pumping water, or by height difference, such as water falling off a cliff, or if you look around your town, you'll see a giant, it's hard to explain, big containers called water towers high above town. And because that water is up there, it has a great deal of gravitational potential energy. So when you open the valves, it will flow down and it will flow through your pipes into your home or business. So that's water. Now electric current depends on the pressure, and that's in quotes because we're dealing with an analogy, exerted by the electric potential difference, or voltage. The greater the voltage, the greater the current. Here's a drawing of a circuit. I mean, it's a schematic. It really doesn't look like this. But an electric circuit is an external path that charges can follow between two terminals of a battery using a conducting material. All right, so where's our battery? It's represented by this, with the longer line being the positive sign and the shorter being the negative. And sometimes people put extra lines in like that. That's still a battery. That's what we like to do because then you won't confuse it with another circuit element called the capacitor, which you'll study in AP2. For this charge to flow, you need a complete and unbroken path. An example of a conductor used to form a circuit is copper wire. So if we go through here, this is all copper wire, goes through the light bulb and comes back to the battery. And don't worry so much about these terms here. The electrons are actually leaving the negative terminal and going this way. But for solving electrical engineering problems, and this is all depends on the way Ben Franklin named which was positive and negative for the charges, we deal with the flow of positive charges even though they're really not moving. So don't worry about that. Again, that's AP2. An example, let's see, continuing the water analogy, one can think of a wire as a pipe for the charges to move through. And here's where the analogy fails a little bit, right? If these were pipes and we were pushing water through, if I cut the pipe here, water would still flow, but it would come out in this direction. But if I cut the circuit here, and it's not connected to anything, no current will flow at all. So again, the analogy isn't perfect, but it gives you an idea of what's going on. The battery then pushes current through the circuit. A battery acts like a pump in the water analogy, pushing charges through the circuit. It is the circuit's energy source. And again, that energy is coming from the chemical reactions in the battery. Charges do not experience an electrical force unless there is a difference in electric potential or voltage. Therefore, the batteries have a potential difference between their terminals. The positive terminal will have a higher voltage than the negative. So what we have here, again, from the previous slide, here's your battery. Let's make that a little longer. Say it's connected up to a light bulb like this. And the current will flow, the charges will flow out of the higher voltage side of the battery down to the lower voltage. And you can also think about gravity that way. If you put a pen in the air, you lift it in the air and you let it go, it will go from a high potential energy down to a low potential energy. And here's a great video from Veritasium about currents. I recommend you click on that and watch it. A quick review of what we just said. Your circuit cannot have gaps, must have a complete path for current to flow through. You need a voltage applied, which typically comes from a battery, that will make the bulb light. That will result in electric potential difference across the battery and drive the charges around the circuit. And the bulb still lights regardless of which side of the battery you place it on. And here's a nice simulator from PHET that you can check out and simulate some of these circuits.